Okay guys, we're back. Ready for the next section, section 7.3. We're actually combining in this section what we're talking about in this chapter, right triangles, with our last chapter, which was similar triangles. And so we're looking at similarity within right triangles specifically. And so if you look at this diagram and try to break this diagram apart into what's going on, look at the big triangle, triangle ABC, the fact that it is a right triangle, and we look at an altitude from there. We look at an altitude from the right angle going down to the hypotenuse. So CD is an altitude here. How that splits the triangle into two other triangles. So there's the original triangle ABC, and then there's two other triangles that get formed here. The small one, triangle DBC, on the right-hand side, and then kind of a medium-sized triangle on the left-hand side, triangle ADC, and then don't forget the original. The original triangle is triangle ABC. And all three of those triangles end up being similar to each other when you cut it with that altitude. So that's what this theorem says. If there is an altitude from the hypotenuse of a right triangle to the right angle, then the three triangles formed are similar. And again, by three triangles, the small one, medium-sized one, the big one is the full triangle. Okay? And it also gives us an example, an actual working example of something we calculated back in the last chapter, which was called the geometric mean. And we told you back then that we would have examples of what that has to do with and so on, because it kind of compares to arithmetic mean and so on. There's calculations you can do, and here's one of those examples. So in this particular case, that altitude that we drew, the CD, that CD is what we call the geometric mean, okay, in the big triangle. It's actually one of the geometric means. So CD ends up being a geometric mean where it splits the hypotenuse. So CD is the geometric mean between AD, one part of the hypotenuse, and BD, the other part of the hypotenuse. Okay, and there are some other geometric means in here and so on. And in class, if we have time, we'll talk a little bit more about the geometric mean part, because we can do this with just strictly similarity as well. Okay, but the geometric mean is an interesting thing that shows up here. So we're just going to look at some examples of how you can compare these three different triangles and how they relate to each other.
I think the skill here, guys, to just add on to what Mr. Scritchfield is saying is you have to be able to manipulate these three triangles, because there's three there, and you got to learn how to make the proportional ratios between which sides are actually the corresponding piece between each of those three triangles. Like, if we look at the short leg between all three triangles, the smallest one would be DB, and it's proportional with the smaller one on the red triangle there, CD,
right,
which is then proportional to the smallest leg on the largest triangle, CB.
Right.
And all those are proportional to one another. And then you can make a proportion similar with all the hypotenuses and all the longer legs. You've got to be able to see that within those three triangles, guys, or this is going to be a tough concept.
Right. Yeah, you got to be able to make those matchups. Short leg in all three of them, the longer leg in all three of them, and then the hypotenuse in all three of them. You got to be able to line those up.
So we'll see that here on the next slide, that you're going to have to do some of that. So right here it says they want us to find y to the nearest tenth. So when you look at this, you've got to be able to manipulate this and say, okay, what's matching up with what, and how can I make this into a proportion somehow? So when I look at this, I see that I have the long leg and the short leg of the middle-sized triangle, okay? So I know that what I need to find is, if I know the short leg of the smaller triangle there on the left, then I could potentially figure out what y is by setting up a proportion, because that longer leg in the small triangle is the short leg in the medium-sized triangle. So let me just put up the proportion here, and it'll make a little bit more sense. So 12 to 18 would be the fact that the 12 is the short leg of the small triangle, and the 18 is the short leg of the medium-sized triangle. And then when I click to this next portion, you're going to see 18 over y, because 18 is the longer leg in the short triangle, and y is the longer leg in the medium-sized triangle. And then, Mr. Scritchfield, do you want to expand on how that turns into the geometric mean right there, or do you want to leave that for now?
Well, notice that the 18 shows up twice here. Okay, and so remember when we calculated the geometric mean in the last chapter, it was the square root concept going there. And so because it was square root, essentially the geometric mean shows up twice in the proportion. And so in the last slide, we said that that altitude that gets created, which in this case is the 18, that's the geometric mean between the two pieces of the hypotenuse that get cut, in this case the 12 and the y. So you put 12 with one of the 18s. It really doesn't matter whether it's on top or the bottom.
Yeah.
The 12 and the y are going to be the means that multiply by each other anyway. So as long as the two pieces of the hypotenuse get multiplied in the proportion, and the 18, which is the geometric mean, gets multiplied by itself in the proportion, it really doesn't matter which way you put them. So 12 is to 18 as 18 is to y in this case, because the 12 and the y are the pieces of the hypotenuse. So whether you see it with similar triangles or whether you see it with geometric mean, you can calculate it either way.
Oh, okay. So what you're saying is that because 12 and y are both part of the hypotenuse, that's what the geometric mean is actually creating, is that two parts of the hypotenuse.
Cutting the hypotenuse in two pieces, and 18 always ends up being, it's just again, just something that works out every time in a right triangle. 18 is always the geometric mean between 12 and y here.
Okay. Now that makes a lot more sense to me.
Good.
Since you said that part about the hypotenuse, about it being part of the hypotenuse of the biggest triangle.
Right, right. The big triangle is what we're looking at, because the 18 is the altitude of the biggest triangle.
Got it.
Right. And as we calculate this, let's go through and do this. We get 12y is equal to 324, okay? And then y ends up being 27. And so if you can picture putting 27 in for that y right there, well, 12 is to 18, that reduces to 2 to 3, right? 6 goes into both, so it reduces 2 to 3. 18 to 27, 9 goes into both of those, it reduces 2 to 3. So that's what that 18 does. That role of the geometric mean is to play like that in-between piece that makes both ratios reduce to the same thing. And it's just kind of crazy that the altitude in a right triangle always ends up being that way, but it does.
Okay. That makes a lot more sense to me now, too.
Good.
Thanks for the description.
Sure.
All right, so here we have another one here, guys. And now they're giving us, we have to kind of create a ratio between the largest one, and then we're going to make one with the smallest triangle. So the middle-sized triangle is kind of null on this one because we don't have enough information about it. So for me, when I look at this, I see that 27 is the hypotenuse of the smallest triangle, and z is the hypotenuse of the larger triangle. And so then I have the short leg of the little triangle, which is 16, but then that 27 is the short leg of the larger triangle. So when I set up my proportion, I'm going to go short leg 16 to 27, which is the short leg on the big triangle. And then I will set up my two hypotenuses, being that since I have the short leg on top, I'm going to have the hypotenuse, which I don't know the hypotenuse for the big triangle on the bottom, which will be z, and then 27 will be on the top there because that's the hypotenuse of the short triangle. And now we're just back to a simple proportion of cross multiplying and dividing, and we get 729 equals 16z, which simplify that again, and we get approximately 45.6.
Doesn't go in evenly. Now this one's kind of crazy in terms of the geometric mean. A little bit harder to remember. The first one, a little bit easier to remember, but this one is a little bit, because we don't have the altitude here. And so it's a different geometric mean. There's actually 3 geometric means that happen in these right triangles. In this particular case, the 27 is the geometric mean. If this triangle was kind of flipped the other way, it would be one of the sides of the big triangle. Ends up being the geometric mean. So the 27 is the geometric mean. Again, it's pieces of the hypotenuse, but it's now the piece that's right next to the 27 of the hypotenuse of the big triangle compared to the whole hypotenuse of the big triangle. So 27 in the proportion shows up twice. The part of the hypotenuse that's closest to the 27 is one of the other pieces. The whole hypotenuse of the big triangle, z, is the other piece in the geometric mean proportion. So 27 shows up twice, they get squared, and then the piece closest to it and the whole hypotenuse get multiplied together to give you the same answer. So again, you could do it by similar triangles, you could do it by geometric mean, whichever one makes more sense to you.
Okay.
Okay, so let's look at some examples here. Here's a little bit more of a real world example, maybe with this tower here and trying to find the length of that ramp and so on and the pieces of this. And so let's look at the big triangle here. We have all 3 sides of the big triangle. Maybe a little bit hard to see there, but the right side is 12.8. The bottom is 23, which would be the long leg. And then the hypotenuse is 26.6 for the big triangle here. Okay, and so if we look at that x being the long leg of the small triangle in there to compare, and of course the 12.8 is the hypotenuse of that small triangle, let's set up a proportion that would have those pieces in it. So the first part of that proportion would be x is to 23, because again, x is the long leg of the small triangle, 23 is the long leg of the big triangle. Okay. The other side of the proportion would be the 12.8, which is the hypotenuse of the small triangle, and then the 26.6 is the hypotenuse of the big triangle. So those pieces fall in place to set up the proportion. If we cross multiply now, we're going to get 26.6x, and 12.8 times 23 is 294.4, and then divide both sides by 26.6 and we get x is approximately 11.11. Okay, you again could do a geometric mean here, but because we don't know the pieces of the hypotenuse, you'd have to call one of them x, one of them 26.6 minus x, or y, use a different variable I guess, and it would just get a little bit messy is all. You could do it, it would just get a little bit more complicated.
All right, now this one, guys, right here is, it's kind of a thing where you're going to have to kind of reach for something a little bit here to kind of make an assumption, but once again, if you can just kind of manipulate these and figure out which of the three triangles do you have enough information on to really set up the proportion, this problem can be done. So when I visualize this, I see that I have the 4 and the 5, which are add together to make 9, which would be the hypotenuse of the big triangle, and then x is the hypotenuse of that triangle with the 5 and the x in it down there at the bottom, which would probably be, I'm getting to guess, the middle triangle here. So I can kind of set up a proportion that x is to 9, maybe,
Which is hypotenuse
yeah,
to hypotenuse.
Hypotenuse to hypotenuse. They did it the other way. So they set long leg to long leg of the big triangle and the little triangle, or the middle triangle. So they've got 5 over x there, which is then x to 9. Okay, so let me rewind here, because the 5 to x, guys, is the 5 is the long leg of the middle-sized triangle, and the x is the long leg of the large triangle, the big one all the way around, and then x is the hypotenuse of that middle-sized triangle, and 9 is the hypotenuse of the large triangle. They just came in backwards than the way I was looking at it, but it still works out. Cross multiply, and now we get x squared equals 45. Okay, and now remember, we did this a little bit last chapter when we were doing the geometric mean a little bit. To undo squared, you're gonna have to square root. Okay, and so you square root 45, you pop that into your calculator, and you get approximately 6.7. If you want to leave it as a radical, it'd be 3 root 5. So.
Right, yep. And again, if you want to look at this one as the geometric mean, if you split that hypotenuse into the 4 and 5 and then see the whole hypotenuse is 9, x is one of the sides of the big triangle, and so x is the geometric mean. So it shows up in the proportion twice. The piece of the hypotenuse that's closest to it is the 5. That's one of the other pieces of the proportion, and the whole hypotenuse is 9. That's the other piece of the proportion. And so that's how you would set it up using geometric mean. Okay, so you're going to have some homework questions here that have you do several of these to make sure that you get the concept here of how these right triangles relate to each other and how they're similar to each other. Okay?
All right.
All right, we'll see you in class, guys.